Hello everyone, my name is Farahani and I'm going to present a review work on new approaches on the stress intensity characterization to be considered in the first virtual European conference on fracture. So this work includes some information regarding the contactless optical techniques resorting to the digital image coloration and thermoelastic stress analysis. In terms of the numerical methods, finite element method and the meshless methods, which is RPIM and NNRPIM, are considered. Analytical solutions are related to the ASTM standard and the concept of the stress-state zone. Two examples are considered: compact tension fracture specimen and the middle tension specimen including central notch. So the presentation ends with the conclusion and the final remarks. So the 3D digital image coloration. So in order to perform digital image coloration analysis, the specimen should be prepared. So on the first image, it is possible to see a prepared image with the speckle pattern on. So in order to perform 3D digital image coloration, two cameras should be considered. If we consider and use one camera, so 2D digital image coloration is, and the halogen lamp should be also used for the illumination, and the deformation profile can be obtained by assessing images captured during the experiment and analyzing the correlated solution, for example VIC 3D. And in the thermoelastic stress analysis, the specimen should be painted in black, and this analysis is based on the temperature variation. So a thermographic camera should be stand in front of the specimen while testing, and the temperature variation will be monitored during the test, which is showing on the image in the bottom side. So the model definition for the first example. So a standard pre-crack compact tension specimen with the geometrical dimension of width equal to 40 and the thickness equal to 2 has been considered. It's an aluminum alloy AA6082 with the tested under fatigue loading condition of 613 Newton by the MTS servo-hydraulic tensile machine in the pure mode 1. The methodology is based on the digital image coloration, and the simulation of the numerical analysis by FEM and by meshless method are considered. The results are obtained from these methods and actually compared to the analytical solution. This is the C formulation from the ASTM, and also Williams series expansion are used in order to obtain the results from digital image coloration and the meshless method. 7 terms has been used in the Williams series for the mode 1, and R and theta are the polar coordinates of the points respecting the crack tip in the window close to the crack tip. So in this slide, it is possible to see the CT specimen in the tensile machine, and also the crack coordinate in the middle image, and on the right side there is the image that it is taken during the fatigue crack growth, and it was captured by the traveling macroscope. So a speckle pattern is really visualized, and also a part of the crack is showing in this image. So the fatigue test was performed, and the crack lengths in terms of the number of fatigue cycles are shown in this diagram. So the minimum allowable crack length according to the standard for this specimen is 3. So for in this study 3.28 was considered, which is related to the 150,000 cycles. The problem was analyzed by the finite element method in Abacus and meshless methods developed in MATLAB. So the numerical model is showing in this image. So for the finite element method, explicit analysis was used in Abacus, resorting to the 4-node bilinear plane strain elements, and the number of nodes and elements is also shown, and also the same thing with the meshless method. Only half of the model was considered due to the symmetry in the meshless method. And this image is showing the strain in the loading direction, to the distance to the notch tip. So for 3 different crack lengths from digital image correction, finite element method, RPM, and NNRP meshless method. So this graph shows that in close to the crack tip, we have a large strain, which is normal because of the crack tip, and it is decreasing from the distance to the notch tip. And the longitudinal stress and strain can be also obtained from all the methods, and a very good verification has been obtained amongst the results in the shape and the quantity. Stress intensity factor has been also documented for all the analysis from DIC, FEM, and meshless method, and it was actually compared to the standard. A very small deviation has been verified amongst the results. The second example is the same specimen, but it was done by the thermoelastic stress analysis. Thermoelastic stress analysis is focusing on the stress measurement, and on the bottom, on the top side, it is showing some stress amplitude distribution for 4 different crack lengths, and on the bottom side it is related to the same images taken from finite element method. Since it is based on the thermal variation, so some equation from thermodynamic is considered here. So the equation was sorted in terms of the temperature, and after that it was showing in the second line the temperature and the principal stress relation, and the thermoelastic stress analysis is going to produce some information regarding the stress amplitude, which is a function of sigma, and it is equal to sigma 1 plus sigma 2 divided by 2, and this is the same as the sigma xx plus sigma yy divided by 2. So this can goes to the Williams series expansion, and through signal value decomposition it is possible to produce this stress intensity factor in mode 1. And this image on the top is showing the stress in terms of thermoelastic stress analysis, and also the bottom is related to the finite element method. A gap was considered after the crack tip, and a path was defined from that gap to the end of the specimen edge. So the stress was monitored from these TSA and finite element method for 4 different crack lengths as shown in the image, and the stress intensity factor has been calculated for all the methods for different crack lengths, and it was compared to the ASTM. A good verification has been obtained, although there are some differences between some crack lengths in TSA and the finite element method. So the example 3 is a different scenario, is related to the polycarbonate middle tension specimen, which has a central notch. So 2D digital image correction was used in this study. So 1 camera was used. It is a unique shell tensile test, and the material properties of the polycarbonate and the geometrical property of the sample is showing in this slide, besides the gripping setup. The stress dead zone concept is a novel concept, not novel, but from this is linking the classic mechanic to the modern fracture mechanic. And so in the image on the left, it is possible to see that triangular is going to be our stress dead zone area, which has the height of beta multiplied by the crack length. And through some mathematical modification, it is possible to obtain the stress intensity factor. So it is based on the compliance function. And the most important part of this stress dead zone is beta, which was defined as 1.2 by the literature, so we also consider this. And the compliance function can be computed as a C, so the derivative in terms of the correctness has been also obtained, and based on the energy release rate, the G factor can be calculated, and since the SS intensity factor is the function of G, so it is possible to directly calculate the SS intensity factor for the stress dead zone concept for this empty specimen. And on the other side, it is possible to collect the digital image correlation data, and after that, by using some analysis in 2D, it is possible to obtain the digital image correlation stress intensity factor, and after that, so standard, it is also possible to obtain the stress intensity factor range, and also in the finite element method, by using the maximum energy release rate criterion, it is the stress intensity factor range, and the table is showing all of them, and besides the deviation, so the deviation is less than 4%, which is quite acceptable. The conclusion of this study. This study reviews the applicable methods to characterize the stress intensity factor. 3 examples were studied under uniaxial tensile and fatigue loading conditions. Contactless optical technique, DIC and TSA, has been used to experimentally characterize the SIF, and the results were compared to the analytical solution and the numerical studies. In order to perform the numerical analysis, the problems were solved using FEM and meshless methods. An alternative analytical solution also proposed based on the compliance function linking to the stress dead zone concept. A very good verification was obtained amongst the results, and this presentation ending, and thank you very much for your attention.